This is a lecture for chapter 13, first lecture after an exam, and this is getting ready for the last exam, exam 4. So homework is available for chapter 13, so you can get started working on that if you want. Come see me in office hours if you want to talk about exam 3 material, review that, look at exam 4 material, or if you want to start thinking about the final exam, come see me. Exam 3 will take me about a week and a half to get that back to you. And this date is quickly approaching, so let me know if you want to talk about the withdrawal date. So the plan, chapter 13, 14, and then 15 is one of the larger chapters, so it'll have 2 parts. You may notice that we skipped chapter 12. We do that to accommodate the lab schedule. We'll come back and do chapter 12 after 15. So you're going to see some familiar terms actually in this chapter. Mass percent. You may recall one of the earlier labs we did a graph and we did percents. 10% sodium chloride, 20% sodium chloride. That was mass percent. Okay, so you've seen that. You've also actually seen this when we've used maybe acid, 6 capital M HCl. That's referring to molar or the molarity of the acid. So we'll talk about these, and then we'll also talk about the conceptual, how do you make solutions. This is a really important focus in Chem 200, and then more calculations. So this is definitely a heavy calculation chapter. It's one of the shorter chapters, so that'll be nice, but it's one of the heavier calculations. But I really believe if you don't have the concepts down, it's going to be very difficult to do the calculations. So let's get started on solutions. This introduction story is is a tragic story, but it really talks about the solutions, the chemistry of solutions of lakes, and the effects of when a lake, maybe you've heard the terminology, turns over, or a large amount of carbon dioxide comes out of the lake. So you could look into that if you want to see a practical example of solution chemistry, how it can really go terrible. All right, so what we're looking at is, as I just mentioned, solution chemistry. So this is definitely one of the most well-studied. Usually people associate that with aqueous or chemistry with water, things in water, and we will talk mostly about that. But please note, solution chemistry doesn't always mean just a liquid, okay? So usually that's what we associate it with. But the definition is a homogeneous mixture. You saw this if you go back to classifying matter, pure substances, mixtures, and then we had homogeneous mixtures. Those are the ones that were uniform throughout. So 2 or more substances are combining. That definition is not new. You've got that. But now we're making a solution. Okay, we're calling it a solution. And just really want to emphasize, it doesn't have to be a liquid. So the room that you're sitting in right now, you're surrounded by air. That's not a pure substance. Air is made up of nitrogen, oxygen, carbon dioxide, other gases. So that's a mixture, but it's homogeneous. So it's uniform. So I really encourage you to think about mixtures, specifically solutions, other than liquids. So a solution of gas, in a gas, the one I just gave you, was air. Some of you like soda water, so that's a gas in a liquid. Liquid in liquid, you can take a substance, alcohol, ethanol, and put that in water, and there's different levels. Some things are more concentrated than others. We'll talk about that, concentration. If you dissolve a solid in the liquid, that's maybe what we're more familiar with. This happens in salt water. You can see the terms here I'm pointing out. Solute, see, that's a shorter word. Solvent is a longer word. The shorter word is the substance that's smaller in the solution, the lesser amount, I should say. The solvent has the larger amount. So we'll go in more detail on that. But you could even have a solid-solid solution, which seems really strange to think about a solid as a solution, but brass is an example of that. So our terms just mentioned, solute, smaller amount, solvent, larger amount. the solution is made up of both of those. So these two make up the solution. Okay, so we'll need to remember that when we start doing these concentration terms. And that's what we want to focus on. Okay, the quantitative. Well, how concentrated is it? You know, if you gargle salt water, I don't like to do this. This is terrible. So I just put a little bit of salt. I just want to get a little bit in there to say that I've done it. Some people will really put a bunch of salt in there. You can just see even maybe the crystals forming on the bottom, but that's a lot of salt, so it's really concentrated. So that's some general terms: dilute, concentrated. But the concentration refers to specifically the amount. How much of solute do you have in the solution? Okay, so that's concentration that we're going to look at. So general terms, just mentioned dilute, concentrated, small amount, large amounts, but we want numbers now. What is the concentration? So you maybe you've seen a water report. If you're in San Diego, you get a water report, and they'll tell you the concentration of contaminants in your water. So you want to know not just, well, is it dilute? Is it okay? Is it really concentrated? There are specific numbers for things that are toxic, like lead or arsenic. So you want to know, the concentration of my water, is the lead less than what they recommend, or is it more than? So very important to know the numbers. So we're going to start with mass percent. Okay, so anytime you see percent, right away be thinking that's per 100, so that's times 100. Okay, so you can see here per 100 grams. So the percent part is that the mass of the solute goes on top, and the solute and solvent go on bottom, and remember, the solute plus the solvent makes up the solution. Okay, so those are terms. Like I said, if you don't have the concept down, you don't have the definitions down, there's no way you can calculate mass percent because you don't know what the solute is. You don't know what the solution is. So mass of solute, mass of solution times 100 gives you the mass percent. So we look at this, and sometimes we're just looking at the numbers, like what is the percent? Is it higher or lower? Or other times we want to use the mass percent. So this is using it as a conversion factor. Okay? So what I really encourage you to do is when you see 23.2%, right away treat that as 23.2, and remember percent is per 100. Okay, so that's the work right there, is converting this 23.2 to 100. But then let's double check, what are we talking about? For a solution that is 23.2% ethanol, so I'll write the abbreviation for ethanol on top. So that's 23.2, and we're talking about mass percent, so that means that's grams. That's mass. This is grams, 100 grams. And remember, on the bottom is the solution. Okay, so the translation, 23.2%, right away should be thinking that's 23.2 grams ethanol per 100 grams of solution. And if you've got one equality, just like we've seen before, this is actually two conversion factors. You could do grams of ethanol over grams of solution, or you could do grams of solution over grams of ethanol, but they both come from this ratio from the 23.2%. So translate that 23.2%. All right, so let's do some calculations with mass percent. So calculate the mass percent of a solution containing 27.5 grams of ethanol and 175 mils of water. So I'll go ahead and pause here so you can work on this calculation. So what you could have been doing during this time is said mass percent. Oh yeah, that's the grams of solute. And my denominator is grams of solution. What makes up the solution? Remember, that's the solute and the solvent. And remember, this is percent, so that involves multiplying it by 100. Okay, so 27.5 grams of ethanol and 175 mils of water. How do we know what is the solute and what is the solvent? Okay, I want to caution you, water is not always the solvent. So just be careful. The way we determine it is the smaller amount. So 27.5 grams of ethanol is the solute, 175 mils of water is the solvent, and you combine those for a solution. Well, remember, we need grams. We don't have grams of water. We have mils of water. That's okay, cumulative chemistry. You may recall, if you have mils and you have density, now you have grams. So in this case, for water, 175 mils is the same thing as 175 grams. So put it all together. We take the mass of the ethanol, divide that by the mass of the ethanol and the water, because that's the solution, times it by 100, and you get the mass percent for this problem. So that's 13.6 mass percent is what we just calculated. So that's just what is the mass percent, okay? Well, sometimes you're given the mass percent, 11.5% sucrose, and you're asked to calculate, use that as a conversion factor. So what volume of the soft drink in milliliters, so we're looking for milliliters, contains 85.2 grams of sucrose. So if we look at this, right away again, I want you to think 11.5 grams over 100 grams. That's where that percent comes from. Okay, so let's take a look. What is that? That's 11.5% of sucrose. So I can label this sucrose. I'll just put the abbreviation of the name here. And we're in a soft drink. So you could say soft drink or just the solution for the 100 grams. Okay, so this is our equality that we get from 11.5%. Right away, we should write down 11.5 out of 100. So we need to see where we're going then. Okay, if we start with grams, okay, again, we have lots of grams here, so this is why I really emphasize, really write down grams of what? Grams of sucrose. If you have 85.2 grams of sucrose, well, then you have to cancel grams of sucrose. So that's here, that's 11.5 grams of sucrose. And remember, now we're inverting the mass percent, so that's 100 grams of sucrose, or sorry, 100 grams of the solution on the top. But the problem didn't ask for grams of solution. It says what volume of the solution, or what volume of the soft drink. And in this case, you're not given a density equals 1, so you have to put in this number to do the calculation. That's 1.04 grams per 1 mil. So our units really help us here. That's, again, this is the formula. Grams of sucrose cancels out grams of sucrose. And remember, we took the percent and inverted it to get the grams of solution on top. The grams of solution versus the mils of solution is the density, so we're dividing by the density. That gives us our mils of solution for that. So this is using mass percent as a conversion factor. So that was mass percent, and you'll see mass percent in lots of different areas: environmental chemistry, environmental science, a lot of places. Molarity is used pretty exclusively in chemistry, and you've already seen it. Moles tells us the amount of substance. Okay, so in this case, we're talking about the moles of the solute as the numerator, and in this case, we're looking for liters of solution. So that's a volume. Okay, not grams like we did earlier. So this is moles of solute, liters of solution, and you can see, again, back to our terminology, dilute, less particles, less of color, concentrated. Look how dark this solution is now. So there's a lot more moles in there You add solvent, you dilute it, less in that small little caption, less amount you can see there. So that's why it's more faint and that more dark. Okay, so let's use molarity. So again, just like mass percent, if we see capital M, 0.500 capital M, I tell this to my Chem 200 classes, my Chem 201 classes. Don't let that confuse you. Rewrite it right away. That's 0.5 moles of sodium chloride, and that's 1 liter on the bottom. So write it out. 0.5 sodium chloride, 1 liter on the top. So we got 2 conversion factors right away that can tell you if it's capital M, and really emphasize moles of solute, liters of solution. So you know if you need to solve for molarity, you can just plug it in, or if then you're going to use it a conversion factor, you know which one's the solute, which one's the solution. Okay, so here's another one. Go ahead and take a look at this. This is calculate the molarity. You're given the grams and you're given liters. Go for it. So as we've seen time and time again, if we have grams, the process to get to moles, that involves molar mass. So that's one quick step away there. And that's looking it up on the periodic table. Sodium 23 roughly, chlorine 35 roughly, that gets you to 58.44. So that's moles of the solute. And you can see here 3 sig figs. 3 sig figs, that's what the underline's for. And then we end up divided by the liters and we get a molarity with 3 sig figs. So that's solving for molarity if you know the moles of solute, liters of solution. So now let's use the molarity. Okay, so you're given the molarity, sodium hydroxide, and you're given moles, solve for liters. So again, I showed this earlier, capital M, rewrite it right away. Moles of solute, liters of solution. And some of you will just plug it in this formula and there's nothing wrong with that. That's great. Okay, what the answer I'm showing you here is dimensional analysis. I really encourage you to be comfortable with this. So you say that's 0.114 molar sodium hydroxide, so that's inverted. Moles of sodium hydroxide over 1 liter, that comes from the molarity. So we're taking the moles, divide by molarity, moles cancel, and that gives us liters of solution. So that's the quantitative piece. The first bit of the quantitative piece, calculate mass percent, use mass percent as a conversion factor. Calculate molarity, use it as a conversion factor. So now we're going to talk a little conceptual, and then we'll come back to some calculations. So we spent a lot of time talking about solubility rules. Does it dissolve? Does it not dissolve? So what we're talking about now is when it dissolves, what's the concentration? Okay, so the reasons first for dissolving is because solvent and solute interact. Okay, we're talking about solutions now, so we have this terminology, and you can see here water is the solvent and it's polar substance. You can see this is showing from our Lewis structure chapter. We saw polarity, partial positive, partial negative. Well, we've seen for a while that ions have full charges. So this positive is attracted, this partial positive is attracted to this full and negative. This partial negative is attracted to this positive. This is why sodium chloride dissolve in water. So as you can imagine, large amount of the salt, sodium chloride, the water is attracted to it. So you can see the oxygens, the partial negatives, are all facing the positive charge of sodium. And over here it's the opposite. It's the hydrogens that are facing inside towards the negative chloride. So that's what happens when you add a solid that's an ionic compound that dissolves. in water, it breaks up and is surrounded by the ions. So we've got free sodium ions, free chloride ions. It's not a precipitate. Okay, so now we've been talking about concentration. Well, what happens? How much is dissolved? What is the amount? What's the amount of chloride versus the amount of sodium? So that's the next piece, okay? Sometimes we need to know specifically how much chloride is in there, how much sodium is in there. So we can do these calculations now based on stoichiometry and based on the formula. So if we know these ionic compounds and it dissolves, then we can determine. Okay, so magnesium chloride has 2 anions for every 1 cation. This anion will be twice as concentrated. Okay, what this means is, think about the reaction. Okay, if we talk about the dissolving process, so it's a physical change, dissolve, put this in water, but we would still balance this like a chemical equation. So magnesium has a positive 2 charge, and it's now in solution. And chloride have a minus 1 charge, it's now in solution. And those came from the solid. Double check, look at the balancing. There's a 2 here. That means there's a 2 here to balance it. So has 2 anions for every 1 cation. So if we think about this now, if we say we have 1 molar magnesium chloride, that gives us 1 molar magnesium, and now is where the 2 comes in. That gives us 2 molar chloride. So the chloride is twice as concentrated as the magnesium. Alright, so now you set it up. You have a 1.50 molar sodium phosphate solution. What's the concentration of sodium? What's the concentration of phosphate? So a good idea is to think about how many ions. Remember when it dissolves, so just like I did before, drawing out an equation of this, Na3PO4, that goes into the ions, and that's Na+. This is PO4, which can be a little confusing, but that's the polyatomic ion. So if we committed our polyatomic ions, then that comes back to help us in this chapter. That's phosphate. Okay, so if we look over here to balance, that takes 3 sodiums for 1 phosphate. And if you look, we didn't start with a 1 molar solution, we started with a 1.5 molar solution. So that's 1.5 molar phosphate. And this is 3 times that. That's 4.50 molar sodium. So if you take a look here, another way to think about it, 3 times the concentration, 1 times the concentration, that's the individual ions, the concentration of the individual ions. So a couple of other things I want to focus on, and then we'll close with a couple of other calculations, is making solutions. So I believe I mentioned that making solutions is critical in Chem 200. It's actually critical in chemistry labs. Is if you're going to do tests, if you're going to analyze reactions, you need to be able to make solutions. So how can you create a certain volume of a solution of a certain concentration? This is an assignment. This is practical. This would be done in CHEM152 lab. I would give you an assignment and say, make this solution 0.5 molar. Go for it. And then we'd analyze and see, is it 0.5 molar? So that's a lab that's coming up. So this is really common skills, really important. All kinds of research labs need to have known solutions, and you can buy some of these, but they're really expensive, so you just make them. That's what you do. You need glassware, specific kind of glassware, and you've seen some of that already in lab. And then you need to follow good procedures and practices how to do this. Okay. So let's start with a 1 molar solution of sodium chloride. How would you make 1 molar solution? Okay, so remember, capital M, break it out right away. That's moles of solute, and that's liters of solution. Okay, so in this case, if you have a 1 molar solution, it really makes the math quite easy as long as you have the necessary glassware. So if we take a look, this is a 1 liter volumetric flask. So you may recall a volumetric flask. It has one line at the top, and that's 1 liter when you get it to that mark. If you go above that mark, you don't know how much you got. If you go below that mark, you don't know how much you got. Okay, so you need the right glassware. It's a nice, expensive volumetric flask. And then you need to add 1 mole of sodium chloride. Well, you can't just go to the balance and say, give me 1 mole. You have to look up what's the molar mass. So in this case, the molar mass is 58.44 grams. And if you need 1 mole, then you add 58.44 grams. What if you wanted to add a 2 molar solution? Okay. In that case, you would take the molar mass times 2. If you wanted 0.5 molar solution, you would take half that molar mass. So we'll do some calculations like that in lab. So you take the solid and you add it to the bottom, and then you add some of the solvent. In this case, it's water, but really encourage you, it's important that you dissolve that solid now. So shake, 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 dissolve, dissolve. If you don't dissolve this and you add all the way to the mark, you come back in 15 minutes or so, it'll dissolve, and then your line's going to be way above the mark. Okay, so dissolve, dissolve, you see it's all dissolved, then you add more water to the mark. That's a 1 molar solution, sodium chloride. So that's one way to make, is you start from the solid and you add it into volumetric flasks till you get to the mark. Another way is to actually do a dilution. So this is starting from a solution that is more concentrated, but you don't need that amount. Okay, you want to use a less concentrated. So you need to go through this process called dilution to get there. So your stock is your concentrated, and you're trying to figure out how much of this stock to use. Okay, so you're going to use an equation to figure out how much stock do I add and how much solvent do I add. Okay, that's the key here. We're just adding solvent to dissolve. So the equation is M1V1 equals M2V2, and really encourage you to be cautious with this equation. Please note this is the dilution equation. So this means you're taking 6 molar hydrochloric acid and you want to dilute it to 1 molar hydrochloric acid. So it's the same substance, you're just getting a smaller molarity, and you're doing that by adding solvent. So I want to remind you, capital M, you've seen this a lot now, is moles per liter. So that's molarity. Volume is in liters. Molarity times volume equals moles. Okay, this is a really important calculation to be able to do. Moles over molarity, moles over liters times liters gives you moles. So what that's saying is the moles on the left, and look, this is molarity times volume, equals the moles on the right. So that's telling us that our solute, the moles of the solute, does not change. What changes is how much solvent you add. Okay, so a dilution adds solvent, but the solute stays the same. So let's take a look at that. This is calculate the volume, and the key right away when you hear dilution, red flag, that's M1V1, M2V2. That's what we think of when we think of dilution. So now we just got to keep track of where's everything at. This is 0.100 liters of 15 molar. So that's one side. And it's asking how much volume to get to the molarity, the molarity. So we're solving for volume 2. Substitute it in, you can see volume 2 equals 1.5 liters. So you take very little, 0.1 liters or 100 mils of this concentrated or of the stock, and you dilute it to 1.5 liters. That's a lot of solvent that we're adding, but you can see that changes the concentration from 15 to 1. So what we just did is making solutions. Solve for molarity, make it directly when you weigh out the solid, or make it from another solution and do the dilution equation. So what we just did is some of the same math we're going to use here for solution stoichiometry. Okay, so molarity is a ratio between moles of solute and the volume of solution. Okay, well that means we can get moles. Okay, so again, a roadmap that you've seen: grams, moles, moles, grams. We could add particles on here. You can do so much now. So what we've added to this, and I'm sure that's so great to hear, we're adding pieces to this. Your molarity can get you into moles. Molarity can get you into the moles down here. So now we do more stoichiometry going through moles. That's the key, that we're going through moles. If you see molarity, that's got to tell you I have moles per liter. Okay, so molarity, that's what it's giving us. So let's do a couple of these together. First one, it gives you the molarity. It's asking for liters, and look, it gives you molarity and liters. So that sounds really familiar. M1 V1 equals M2 V2. Where's this equation for? This equation is not for stoichiometry. Cross it off. This equation is for dilution. Okay, we've got to do stoichiometry. That's a member of the roadmap. Moles to moles. Okay, well, we're not in moles, we're in molarity. But if we have molarity and volume, remember that's moles per liter. That's liters. We actually have moles. Okay, so we can get moles in one step. And if you have moles of lead, and that's here, 1 mole lead nitrate, and 2 moles here. So now we can go moles to moles. That's our stoichiometry, right? So this is volume, molarity. Stoichiometry is 2 moles of Ki on the top, 1 mole of this lead nitrate on the bottom, and now we're in moles of Ki. But that's not the question. The question was volume. How much of this Ki? Well, you're given molarity of Ki, so look at this. We're dividing by molarity of Ki because we have moles of Ki. If you have the moles of Ki from stoichiometry and you have a molarity, then you have the final answer in liters. So this is liters Ki here. So let me just double check this one because some of these are coming through incorrect, the labels. So 0.104. Sorry, I didn't see this before. So the answer is correct, 0.407, but remember the question was asking for how much in liters, so it got dropped off here somehow. That's 0.407 liters of Ki. That's what we're looking for here in this problem. So the reminders, this is not a dilution, not an MV, but we used volume, we used molarity, and we used another molarity. So it definitely looks like that, but MV does not account for this mole-mole ratio, which in this case was 2 to 1. So you have to do this or you'd have the incorrect answer. So the last one we got here, now we're changing up a little bit. We've got milliliters and a molarity, and we've got milliliters and a molarity. So again, M1 V1, M2 V2, no, definitely not. Okay, this is not a dilution, so we can convert our milliliters. We're given 27.2 milliliters. And just go to liters, okay? Metric conversion, that should be 1,000 here. 1 liter, and this is of the nitric acid, so that's the liters, so then that's 0.135 moles of the nitric acid. And that's over 1 liter. So if you're in moles of nitric acid, then you got to go to the balanced chemical equation and see that's also a 2-to-1 ratio. So if we used M1V1, M2V2, we get the wrong answer. So that's 2 moles HNO3. And on top here is moles of the sodium carbonate. Okay, so we've got moles. Now in this case, we're given the question of calculate milliliters. Well, you have molarity still, so we want to invert molarity. That's 0.112 moles over 1 liter of this sodium carbonate. So we've got all our stuff set up here. We're just one step away, and that's milliliters. Well, what I want to emphasize, which is kind of risky because I've really emphasized moles per liter, but take a look here. If you're in milliliters, you divide it by 1,000, so that's milliliters canceled. And over here, you're going to multiply by 1,000 milliliters is what you're ending up with. So really, if you divide by 1,000 and multiply by 1,000, you actually didn't need to do that. You could take your milliliters times your molarity, so that's volume times molarity. This is the key, okay? What I really want to emphasize here, you've got to have the mole ratio, and you got the mole ratio. Now you can use the other molarity to get to this volume, and should end up with 16.4 mils. So come see me if in office hours if you want to talk more about solutions and chapter 13 concepts or calculations.